Katherine Freese is a renowned theoretical physicist, a professor of physics at the University of Texas at Austin, and a member of the Simons Observatory. She's one of the most acclaimed scientists of our time, and she's recently made headlines again, claiming to have found the first evidence of dark stars, putting us one step closer to figuring out what the universe is made of. Join us for a sip of Katie's intoxicating cosmic cocktail.
Cosmetology meets cosmology. Today's a special episode for me. It's not all the time I get to interview not only one of my friends, not only one of my collaborators, but one of the most renowned scientists that exists today, and that's Professor Katherine Freese of the University of Texas at Austin. Welcome, Katie. How are you enjoying San Diego?
Thank you, Brian. I'm having a great time.
It's always great to see you. It's great to have you back for your second appearance on the podcast. The first time you were on was for this just amazing book. I mean, there aren't too many books that, I read cover to cover in science, because a lot of it, you and I are experts in science, so we don't really need to know much of the scientific content. But this was so much fun. I read the whole thing, and I really devoured it and digested it, and we're going to get into the hijinks of it, maybe as a recap for people that haven't seen it. I might re-release or link to the episode when Katie was on 2 years ago. It's amazing. But it's pertinent today. We have now Simons Observatory branded merch, which you can get for $100 million or so. This is a bottle of whiskey for your next cosmic cocktail, Katie. That's hard to say. And since you were last on, a lot has happened to the Simons Observatory and for your in your career, and we're going to talk about all that, including this mesmerizing, mystifying concept called dark stars, which may have been detected. We'll talk about that with this device that's up front right there, the James Webb Space Telescope.
There it is, the James
My student
Webb
3D
Space
printed
Telescope.
it. But first, let's start with big news, sad news in a way. About a year and a half ago, you tried to connect me with Professor Steven Weinberg, and since then he passed away. He actually gave a lecture of the same kind of honorary lecture that you're giving here, Dash in Memoriam. He did it remotely because it was near the end of his life, but you're here in person, very much alive. Talk to us briefly about Steven. What did he mean to you? What is that? What is it like being the director of the Weinberg Institute? Is it Weinberg Institute, or what do we call it?
It is, yes, it's the Weinberg Institute for Theoretical Physics. And it is in honor of Steve Weinberg, who was the greatest physicist of our time. There's just no question. I think pretty much everybody agrees. So he was the theorist behind much of the standard model of particle physics, the quarks and leptons, and how they merged together, especially going to higher energies and back in the early universe. The forces of nature unify together, the electroweak theory, and can I also say he was a friend?
Yeah.
One of the kindest people on this planet. He was wonderful.
He was, as they say, a mensch. He was one of the few Nobelists that I didn't get a chance to interview. Sadly, we'll never get to. I had his co-laureate, Shelley Glashow, on, and they were basically in a friendly competition since they were in high school together. It's just amazing.
Bronx Science.
That's right.
Yeah.
All the way up to Cornell and Harvard, and their careers were so intimately intermeshed. And Shelley, thank God, is still very much alive and with us, and sharp as a tack. But I wonder, what Stephen might make of, some of the discoveries that have happened just in the last couple of years. And in particular, things that we are partnering on with the Simons Observatory to try to uncover, you from a theoretical angle and myself and my team from experimental angle, and then kind of co-meshing them together. So is it not the case that we know now that we know less about certain things in the universe, including dark matter and especially this Hubble tension? I've been just dying to ask you about that. So where do you come down the Hubble tension? What's the answer? Because I look to you for the most erudite advice on these matters. So Katie, tell us, what is your take on the Hubble tension? Is it for real? Should we just ignore it? Is it a fad? What do you make of it?
Well, I think it's really important. So the trying to learn about the expansion rate of the universe from data from the cosmic microwave background, which comes pretty early in the history of the universe, or from supernovae that are more recent. And it seems that these numbers are discrepant at 5 sigma at this point. So the Hubble constant, based on this earlier epoch, is lower than the Hubble constant 67 versus 72. Now, putting it in a broader historical perspective, when I was in grad school, there was the camp that said it's 50 and the other camp that said it's 100. And so now we're arguing about 67 versus 72. So is it possible that there's something going on on the experimental observational side that will resolve and everything will meet? I don't know. Wendy Friedman seems to think so. So I don't know. Is it an observational problem? In the meantime, as theorists, we get to have fun trying to explain this.
When I think about Katherine Freese, I think about your taste, and you have exceptional judgment and taste, and you're always seeming to be, where the puck is going. I had Adam Reese in that very chair about 5 months ago, and he gave a distinguished lecture, much of the kind that we're looking forward to you're giving later on today. And there's a notion that, maybe there are 1,000 flowers that can bloom theoretically, but from an observer's point of view, they seem to get really entrenched in different explanations. And I spoke to your, friend Mike Turner recently. The episode hasn't aired yet, but by the time this one does, it might. And we talked about, what are the known knowns about things like the Hubble tension? So not exotic. Things like magnetic fields. We know magnetic fields exist. Do you have a favorite explanation, or is that kind of a non-scientific way to think about it? Like, should we have favorite explanations? Should we be married to our ideas about theoretical models that could explain it? Or should we just be open and, kind of see what happens?
So my attitude is always we should be open to see what happens. But there's a lot of ideas that fail. They get ruled out. And so then you move on. Mm-hmm. And the question is if you're going to introduce new physics, would it be before the time of the cosmic microwave background? Would it be after the time of the cosmic microwave background? And I think everybody agrees that the later stuff is much harder to work with. Mm-hmm. And so I thought particularly interesting, I think, is the idea of early dark energy, where you would have a vacuum component to the universe that it never dominates, but it's important just before the production of the cosmic microwave background. And it would come in as a constant vacuum, which suddenly disappears at exactly the right time. And I'll tell you, I saw that and I thought, oh my God, that looks like a phase transition to me.
Yes.
So we've been looking at first order phase transitions as possible explanations. And that would be where you make bubbles of the new phase, kind of like boiling water. Mm-hmm. And so this is, it's a possibility that would be an explanation. We called this one the chain early dark energy. Mm-hmm. And so that got us interested more generally in bubble collisions and how they might actually show up in the bubble collisions lead to gravitational waves that you could see. So there's a prediction there.
And how would they agree or be in tension or compete with the primordial B mode polarization that we're looking at, the waves of gravity that generate those phenomena?
No, they not in the same frequency range, not showing up in the same way. So
could you see them with like LIGO or
yes,
LISA?
You could see them with things like LIGO, or if they're different, not the ones for early dark energy, but more generally, you could nanograv has stochastic gravitational waves that they've just recently confirmed.
That's right.
And is that due to supermassive black holes colliding? Mm-hmm. We don't know. Or actually, what might fit the data better would be bubble collisions from first order phase transitions in the universe. Mm-hmm. And so we're exploring that possibility.
When I first saw, kind of the initial data from BICEP back in 2014, 2013, when we started to have an inkling that we were onto something, it never really occurred to me the kind of uproar that it would stir up. And of course, I wrote about that in my first book, Losing the Nobel Prize. But
so have I talked to you about the uproar it did to me?
I want to talk because I remember I did get an email from you, and I did see things like that around the time when the rumors were kind of percolating, along with many of my friends and colleagues. So tell me about the uproar. I actually haven't heard this from the direct party involved. So please tell us, Kate.
We have a model called natural inflation.
Yes.
It uses a particle, an axion, as the particle that's responsible for inflation. And the idea of using axions for inflation, I thought it was a great idea back then, because how else are you going to explain this bizarre situation where you have, it's a really good idea. And since then, it has been picked up by lots and lots of people, different variants of it. Mm-hmm. The original variant, well, we had very specific predictions for what it would look like in CMB data. And when this original short-lived discovery happened. It was a perfect match to our theory. So I went through the roof, and we all I was at the University of Michigan. We all got together in a giant room to talk about what the new discoveries are, and I was like going, yay! So, but the basic idea still holds up, even though not that original simple version.
Explain for the audience that may know. I mean, I have the most brilliant audience in the known universe, I always say, but explain for my audience that may not be familiar, what is an axion, and what does it have, if anything, to do with inflation, rather than being a putative mechanism for dark matter? That's where they've heard about it primarily on this channel. Okay. So what is an axion, and how can it be related to inflation at all?
The original axion was the brainchild of Steven Weinberg and simultaneously of Frank Wilczek, both Nobel laureates.
Frank's been a guest.
And though that idea would be a particle that would solve problems in the theory of strong interactions. And so that is the dark matter candidate that people are very excited about and looking for. However, the word axion, I'm going to put quotation marks around it now, is used more generally for anything that has similar physics built into it. So what we need for inflation in particular is we need, this is a potential for the vacuum energy, which it's a very, very flat potential. And so it needs to be very wide, but then it needs to be short. You need to have you have to have lots and lots of E-foldings of inflation. The universe has to inflate for a long time. But inflation also produces density perturbations, which we see in the CMB, and you can't overproduce those.
That's right.
So the beauty of the axion is that there's a reason for two different scales in the problem. Most particle theory, you only have one, and so the height and the width would be the same. But if we use an quote-unquote axion, modeled after the physics of the QCD axion, we have a really good, a literally natural candidate for inflation. So that's what our basic idea is. It'd be higher energy scales, important earlier in the universe, but it's the same on theoretical grounds. We're writing down the same things.
I see. Now, I don't have a really strong opinion about the following quote, but I've heard it said, I'd love your reaction to it. A theorist only has to be correct once in her life to make a career, outstanding career. An experimentalist only has to be wrong once in his or her life to ruin his career. Now, I'm probably a counterexample to that. What do you make of that? Do theorists, have a propensity to kind of swing for the fences, and if something sticks, then so be it. But there's sort of what I call lack of quality control, an overabundance of theory. Or do you think it's really more on a parity that actually both experimentalists and theorists both have to grapple with quality and quantity in equal measures? So what's your take on that silly quote?
Well, let me start talking about on the theory side, because it's something I know more about. We have to, we whatever we do, we can be creative, and that's what I really enjoy doing, sitting around the table, batting ideas around with people, and then you have a flash of insight. Wow, we've got to try this. It has to be consistent. It has to be self-consistent mathematically. It has to be consistent with all the data that are out there. And if you violate any one of those things, and if you make a big mistake and you put that out in public, you could really hurt your career too, just in the way you said an experimentalist could. So that's not something I've ever done. I've been I think I'm known for having a lot of ideas, and I'm very careful. Most of them die within 10 minutes or maybe within a week, but having them stick around for 30 years, that's pretty cool. And I guess I remember in grad school, one of my professors saying, if you have a paper that's still quoted 10 years later, you're doing well. And so I guess that's the standard that I live by, and so I'm doing pretty well.
My thumb's rather occupied right now holding up good old Carl Sagan, but yours is free to push that like button. And don't forget to subscribe. It really helps us with the algorithm. Now back to the episode.
One of my favorite things about how you operate, shall we say, or the things that really speak to me about your brand, the Katherine Freese brand, is that you love working with experimentalists. And in fact, without you, the Simons Observatory may not have gotten to the level that it's at, because you've been an instrumental, no pun intended, supporter intellectually and logistically, financially, et cetera, et cetera. How do you choose of all the things that your portfolio could allow you've had some just outstanding, successes in your career that have led to tremendous leadership opportunities for you. How do you choose as a leader where you're going to put your institution's finances and the most precious resource, their intellectual capital and attention? How do you allocate that as a leader?
Well, thank you for the compliment. And I have always looked for physics that you can test. And I mean in my lifetime, not 300 years from now.
Yeah.
So I work on dark matter that you can test, that is being tested. We're behind some of the tests that are going on now.
Yeah.
And also on inflation, when we realized you can test this, and it's very, not just the idea of inflation overall, but individual models are testable because of the density perturbations, because of these primordial B modes that Simons Observatory is really gunning for. And that is, frankly, why I got all excited about CMB experiments, because I thought, we're going to get the B modes. We're going to prove that natural inflation is right. I was all into it. And so then the funny thing is, there's another piece of physics that I also have, my very first paper ever, the bounds on neutrinos from cosmology. So the idea that you can go after neutrino mass with cosmology.
Yes.
And all of a sudden, I was writing, I hired a postdoc, Martina Gerbino. She's also a leader in Simons Observatory now. And we were writing a bunch of theory papers and comparing to data and da-da-da-da-da. Guess who can go after that? Simons Observatory. So when
I know,
so
dark, whiskey,
we can go after dark matter. We can go after so much.
Planet 9. All these things. That's
so that's why I really wanted to get involved and started hiring postdocs, students, lots of people, and most recently at UT Austin, your former postdoc, Nick Galitsky, is doing great at Texas.
Show a picture of him here. Yeah, good old Nick Galitsky.
Yeah.
I gave him a shout out on Joe Rogan when I was on it. I think I gave you a shout. I'm going to get you connected to Joe Rogan, and hopefully Lex Friedman, both of whom I've become friendly with. Let's turn back to this book. In addition to such cool topics as a DNA dark matter detector, which you and the president of the Simons Foundation, I believe, David Spergel, worked on many a year ago.
Yep.
The aspects for detecting dark matter, as you say, in not only in your lifetime but in your careers, golden years that were, I won't say golden years, but just most productive years, when you're making hay, so to speak, while the sun is shining. I came away a little bit pessimistic. I mean, the subtitle is 3 parts dark matter. I came away a little bit pessimistic from this book when I read it, and I've revisited it recently. Let me move the CMB beach ball so people can see it. That perhaps it's a long shot, but at least it's not as big a long shot as dark energy. When I sat here, when Adam Reese and I were sitting there, it just seems like there's almost no hope for dark energy, coined by, as I said, Mike Turner, who you'll see that episode soon. But even Mike seems to agree that we know almost nothing about dark energy. And where do you stand? I mean, we're going to get into dark matter, dark stars, etc. What is the other parts of the cosmic cocktail? What do you make of that? What the heck is going on? Who ordered that drink?
Yeah.
Dark energy. What the heck?
Yeah. So 95% of the universe is the dark side, and 70% is the dark energy.
Yeah.
And at this point, you might as well call it gobbledygook because we know so little. Well, I will tell you a story of my involvement. So I remember when people started. The idea of dark energy was named dark energy all of a sudden, and then all of a sudden it's going to be parametrized in terms of the equation of state W. And I'm sitting there thinking, whoa, wait a minute. The observers are going to specifically look for this one thing, but how do you know that's the right way to parameterize it? Right. And so I was at a meeting in Chicago. I was out in the halls. All of a sudden I had this inspiration. Wait a minute. What if you don't need any dark energy at all? What if it's only matter and photons and so on. So that's all there is. There's matter, there's photons, and there's nothing else. But the equations change. The equations are different. And I'd been working with a postdoc, Dan Chung, on extra dimensions. So there could be, in addition to our universe, our 3-dimensional universe, sitting as a membrane in many other dimensions. And there could be another 3-dimensional membrane somewhere else. And the effects of this extra dimensional stuff is to change the equations governing the evolution of our universe. So Einstein's equations as applied to our universe, the Friedman-Robertson-Walker equations, there would be an additional term. Okay. And so we had thrown around, well, you don't know what that term is, but what if it's such that it only becomes important recently in the history of the universe? It causes acceleration just with matter and radiation, photons, and so on. No dark energy. So I had that idea, and I probably foolishly called it Cardassian cosmology. So I still think that could be true. That it's Einstein's equations that need a. Now, since that time, that was 2002. So then, since that time, a lot of people have played around with a lot more sophisticated modifications of Einstein's equations, disformal gravity, Galileons, and most of those ideas have been ruled out because gravitons that move at the same speed as light, pretty much. So those ideas have mostly died. So that I still think is an interesting direction, but I kind of stopped working on dark energy. It's too hard.
Yeah, it seems just hopeless.
Too hard.
The more, as your colleague, late great colleague, used to say, the more we learn about dark energy. To paraphrase him, he said about the universe, but he said the more we learn about the universe, the more pointless it seems. The more we learn about dark energy, it seems mostly pointless. Do you ever think about the philosophical or the theological even implications of your research?
Sure. I think most of us in cosmology thought about it, and it's part of why we do what we do. Now, there's the question: is there God, or is there not? And how do we? I think cosmologists, some are automatically atheists. No, we're doing laws of physics. We're writing down equations, and that's all there is. Others are very religious, and well, that tells you something, that you could this entire spectrum is possible and still be doing cosmology. And so where do I stand on this? I'm not sure. And how does it there's some questions like, what is the origin of time? Does that have something to do? Is that a physics question? Is that a metaphysical question? In my heart, I believe all these things are physics questions, and that we'll get somewhere with them.
And similar to the multiverse, what are your thoughts there?
Not crazy about it.
Me neither.
I feel like it's chickening out. It's not chickening out, but you're not answering the questions that you're supposed to be answering, which is, why does the fundamental constants have the value they do? Then yes, I know. If you change the value of E, the electric constant, by one tiny, tiny bit, then we all disappear because our nuclei don't hold together.
That's right.
Yeah, well, that doesn't mean that we happen to live in somewhere in a multiverse that has the right value. I don't buy that. I'm sorry. I want to know why it has the value it does.
That's right. Yeah, and I think these are kind of the questions that should plague people. I find oftentimes my students don't think about these things, that they got into cosmology because they're really good at building instrumentation, working on dilution refrigerators and vacuum systems, or they got into because they're really good in theory and calculating, and they love doing homework problems as an undergraduate, and this got them into it, and they're creative and they want to think about things, but they tend not to really address the, as Roger Penrose calls it, the mastodon in the room, which is, what the heck is going on with the origin of the universe. On the other hand, though, Katie, I wonder how you react to this. If I study, my biology colleagues, that gave me this brain and everything else, like, their job as biologists is not to explain, like, the origin of life, right? I mean, some work on that, but that's not their job. So why, as cosmologists, should we think about understanding the origin of the universe? Maybe that's a cop-out. I don't know if you want to react to that. If not, we can move on. But it's important to think about the big picture topics.
Yeah.
Maybe I'll segue into another direction briefly. And that has to do with you as an educator. You're not only, this world famous theoretical physicist, contributing for in so many different fields, from machos, dark matter. Today I learned about axions and inflation. But you're also an educator, and I think of you like that. And I've learned a lot from you, not just from your wonderful popular works and books and appearances and so forth, but also from your papers and seeing you lecture, as we're going to be treated to later today. What's your philosophy as an educator? Who do you look to? Do you have role models, mentors? How does someone become a teacher of the caliber that you exhibit?
I feel like as I teach, as I get more and more experience, I relate to students better and better. And I even teach classes of non-science. Right now I'm teaching a class to non-scientists.
Really?
And it's maybe the only class they're going to take in anything related to physics or even the hard sciences sometimes. And it's my job to get them excited. That's, I think, the main task I feel in this particular case. And I've learned that if I tell stories, personal stories, or stories about Tycho Brahe or whatever, that they have a lot of fun.
Galileo.
Oh, there's Galileo.
Yeah,
okay, so
right.
you tell stories about people and you bring it down to earth, and they really have fun, and they engage, and who knows which one of these is going to become a politician who votes on whether we get funding or not. So I feel like that's one of my tasks, my jobs. And I've always thought it was my job to mentor young women. So I've always made a lot of effort there. Initially, it was really assistant professors around the country who would call me, that we would talk, and I would advise them on, when you have a job interview, here's what you should expect or whatever. And so I've always taken that very seriously. I think that's part of my teaching role.
Yeah.
And I had an undergraduate who I think she's outstanding. So I told her, hey, why aren't you applying to grad school? Oh, I hadn't thought of that. And so now she is, And
was it Jan 11?
Jan 11 was my very first graduate student.
Past guest. Yep.
Yeah. She's
Phenomenal.
pretty awesome.
Yep.
Phenomenal.
She sure is. Love Janet. And she also exemplifies that trait of giving back to the public as well as to your colleagues and to your career and what you do.
Well, that's another aspect of it's not teaching, but outreach.
Yeah.
So I think that's a really important thing that we have to do. And so I give lots of public lectures, TV, radio, panels, and I think and podcasts.
Yeah, that's
so I think all of this is really important for us as scientists to reach out to people who want to know what we're doing.
Yeah. And pay our salary. I always joke, if you worked at a paperclip making factory and your boss came in and said, yeah, what are you doing today, Brian? And said, it's very, very complicated. It's very arcane and abstract. You can't understand it, boss man. So just leave it to the expert. You'd be fired the next day. And yet we expect the public to just keep shoveling money towards us because we're so smart. And sometimes I do get this comment, and I've gotten a lot of heat from this on Twitter and other places where you should follow Katie also, Katherine Freese on Twitter. But the notion I said that, it basically should be part of our education, public communication, outreach.
Yeah. Oh, yeah.
And I always hear, oh, no, scientists, Sabina Hasenfelder, many time guest, no, scientists should just work on what they do, and we need people to do. And I said, look, Sabina, if you want to continue to do what you do, you have to at least give some ROI, return on investment, to the public that pays your salary. Otherwise, not only jeopardizing you specifically, but the notion of scientific education among the public. And she said, oh, it's too hard. Well, okay, you know what's hard? Also, quantum electrodynamics is really hard. Working on inflationary potential is really hard. You weren't born knowing that. You learned how to do it. So anything you feel important, you should learn, including communication. I'm not saying everyone should be Neil deGrasse Tyson or Katie Freese, but everybody should have at least some exposure to the so-called soft skills. Anyway, I'll give you a reaction to that.
When I actually advocated for a course where, if you think about it, this is something that's not taught. So you're supposed to go out into the world and you're going to be judged immediately on how well do you communicate what you do.
And you get no
training. No training? I think that's insane. So I actually did create a course where people would give talks at different levels, and I brought in speaking experts. I brought in breathing experts because all of this matters.
Can I take this course?
Yeah, isn't that great? And I created a syllabus that actually went around the country, and other people used it. But in the end, then you're told, well, this isn't really hardcore, and we really need you to teach something more substantive,
rigorous, right?
More rigorous. Yeah. So that course kind of died, but I think I'm really believe in it.
That's what Janet told me too. She said, when she was writing her first book, they were like, don't do it. You're not going to get a job. She didn't even have her job at Barnard. But then her second book or something, they said, well, we're not going to, you can write it. We won't punish you for it, but we're not
ridiculous.
I had the same thing. I had a Nobel laureate, the son of a Nobel laureate who's no longer here, so I can speak about him. I love him. He loves me. But he used to say things like, we won't hold it against you, but we're not going to give you any sabbatical time. We're not going to do anything for any of my books. And so I've done it, in my summer, when I'm not getting paid by the university. So that's when
I'm asked, would you like to write another book? And I'm like, well, when am I supposed to do that?
Yeah.
It's tough.
Yeah, especially with all the stuff that you're juggling there. Yeah. Let's get to the really exciting stuff that just, as soon as I heard it, I didn't even have to look. They said that Leibniz once got a paper and he was asked to review, it was about calculus or something. And the author was anonymous. And he said, it's Isaac Newton. They said, how do you know? And he said, I know the lion by his paw. So I knew the lioness, when I saw the dark stars, when I saw JWST. First of all, talk about this. This is my brief that I got from one of my sponsors, Ground News. Dark stars are a proposed concept in which the first phase of stellar evolution in the universe is powered by dark matter heating instead of nuclear fusion. Yes. And then I read the preceding the National Academy of Science paper, which is one. Not only does Katie, do the hardcore stuff, but your writing is phenomenal. And did you do Well, let's get into that later. I don't want to keep just sing your praise. I'll be here all day. But talk about dark stars are formed at the centers of proto-galaxies, and the sufficient abundance of dark matter serve as their heat source. Where do these things come from? Are they just like, let's fit the data, or like, have you been thinking about these for a long time?
All right, 2007.
Wow.
I was a Miller professor at Berkeley as a visitor. And Doug Spoliar, former Michigan undergrad, had started grad school in Santa Cruz and said, I want to do a project with Katherine Freese on something to do with dark matter. And after many iterations of throwing the ideas in the garbage because we were so frustrated, well, something good came of it. And we involved Paolo Gondolo as well. And so the idea that the very first stars that form 200 million years after the Big Bang inside these proto-galaxies that will later merge together to make galaxies. And what happens is you have, at that point, the only thing existing is hydrogen and helium from the Big Bang. You have you don't have any other elements around yet. So that clouds of hydrogen start to collapse inside this very centers of these proto-galaxies.
There's molecular hydrogen.
There's molecular hydrogen. Yes, these clouds start to collapse, and in the standard picture, they get to be really, really tiny, and then fusion kicks in, and so on and so forth. And we just asked a simple question, but at the center of proto-galaxies, there's a lot of dark matter. What does that do? And the answer is that the dark matter, let's say it's some type of dark matter that annihilates, these particles annihilate among themselves, such as weakly interacting massive particles, or some types of self-interacting dark matter. So if the dark matter annihilates, the annihilation products, they collide with the hydrogen and they get stuck inside this collapsing cloud. So all of a sudden you're dumping all the energy that was in the dark matter and you're dumping it into the cloud as a heat source. So we realized, okay, well, that's going to stop that cloud from collapsing. And then a year later we realized, oh my God, it's an actual star. It's really satisfies the 4 equations of stellar structure. It's in hydrostatic equilibrium, where gravity is balanced by the pressure, all because we have this dark matter heating going on and so forth. And they become, they initially start out about the mass of the sun, but how weird, they're 10 AU in size. 10 times the distance between the Earth and the sun. Big, puffy, cold. There's no fusion. There's not hot anywhere. Dark matter annihilation doesn't care how hot it is. Mm-hmm. And that means that more mass can fall onto them. So they grow and grow and grow, and they can grow to become 1 million times as massive as the sun and 1 billion times as bright. It's just, we're telling you, it took us a couple of years to put all these pieces together. Mm-hmm. And at this point, John Mather, the Nobel laureate, who
two-time guest on the podcast,
creator of the James Webb Space Telescope, and John Gardner, PI of one of the instruments, they say to us, come on, this is a cool idea. Tell us what we're going to see. What should we look for? And that was 2010. And so my grad student at the time, Cosmin Illy, he did it. We figured out, okay, what are these spectra? What are these things going to look like? And guessing how many there could be, that's hard. But so we were waiting for the data from the JWST. And when it came out, we knew exactly what to do with it because we had planned on this, So
when the data came out, recently announced, there was a claim that there were 2 galaxies potentially that might harbor these objects. 10 AU, it sounds big, but a redshift of 11, it's infinitesimally small. So how can you be sure? How could one verify or refute that these galaxies themselves harbor these massive dark stars within them?
Well, one dark star would be as bright as an entire galaxy containing lots of smaller stars. And the way to tell the difference will be, let me back up. JWST has 700 objects potentially from the early universe, probably, but you're not really sure until you get spectra, the brightness at different frequencies. And so they had, at the time we wrote our paper, they may have more now, but there were 9 with spectra and that were absolutely confirmed as being early universe objects. And of those 9, 5 had publicly available data. And so we looked at those. And 4 in particular interesting, the JADES objects, James Webb Extragalactic survey.
GSZ11-0. That's such a beautiful name.
These are so of those 4 objects that had spectra, 3 of them are consistent with being dark stars. And what I mean by that, so the spectrum of any star, it's a black body. It goes up and it goes back down in a very well-defined way. And our stars would be made only of hydrogen and helium. So that's all you would see information about. That's all that you would see. Whereas these competing galaxies, they have also later generations of stars in there. So that's processed. So you'd see carbon, nitrogen, I don't know, neon, whatever. And so down the road, when we get clean spectra, then we'll know which it is.
How can you differentiate? So I would imagine these could be confused with other objects that are also, to my knowledge, not discovered, but are part of the panoply of research portfolio for Webb, which is called Population 3. Am I right that we have never discovered something that we know for sure is Population 3? And then 2, how would you distinguish a dark star from a Population 3 object?
So the Population 3 objects were when I was telling this picture of the collapsing hydrogen clouds, and that is the standard formation of the Population 3 stars. And they are hot. They have fusion. So they can't grow very large. They can grow about to 500 times as massive as the sun. We're talking about 1 million times as massive. So our guys are a hell of a lot brighter.
Right. I see. So that would be a way to distinguish.
In fact, the only way that we're really going to figure out what's going on is probably not the current objects, but many. I mean, James Webb is just getting started, and so there will be many more objects coming in, and some of those will be magnified by lensing. In other words, they'll look brighter, and you'll have more information because there's stuff in front of them that amplifies the signal.
If you have just an ordinary like Lyman alpha cloud or just some primordial hydrogen cloud, molecular hydrogen cloud or other configuration, can you still form these dark stars? Like, could there be some forming in the Milky Way or somewhere, or they only form in the primordial universe?
They're as soon as you get other chemistry going, it's different. So we're talking about the hydrogen and helium only.
Only, right. So you couldn't do it from pre-processed.
Well, I mean, no, you can't do it from processed stuff, but what if there's some void that hasn't had any action?
That's right.
Maybe somewhere in there they're still sitting. There's still a few forming in there, but
so we wouldn't expect to see one floating by in the Milky Way or something, right? I see.
No,
okay.
Too bad.
So these objects are really captivated the attention in the media, along with
Reuters picked it up.
Reuters, New
Once
Scientist.
Reuters picks it up, everybody picks it up. Scientific American, front page article on New Scientist.
It was incredible. Yeah, it's beautiful. We'll show the cover article of it on our on the B-roll footage if you're watching on YouTube, where you can find me, Dr. Brian Keating, but also find Katie on Twitter and many other interviews that I've done with her, and she's been featured before. So I want to talk about another thing that might be concomitant with this discovery, and this is the so-called claim that is proffered about the same media in some circumstances, unfortunately, New Scientist or phys.org, that either the Big Bang never happened.
Oh, I think I know what's coming, yeah.
Or the universe is 26 billion years old, not 13 billion years old, including by a gentleman, Rajendra Gupta, who's in Ottawa, who's I've been in contact with about maybe he'll come on the podcast and come to visit us. But anyway, tell us, what is this connection? What do you make of these claims? Because I'm old enough to remember 1996 or whatever when Hubble Deep Field came out, and you heard the same kinds of things. These galaxies are too mature to have spiraling arms and so forth and have this grand design. The universe must be much older. In fact, it must be infinitely old or eternal. What do you make of these claims? Why are they so eye-catching and clickbaity for the media?
Well, I mean, sure, it would be exciting if we'd been getting everything wrong all along, but you know what? I don't think we have. Brian, I'll turn to you.
Yeah.
You're the CMB guy. You tell me, what's the age of the universe?
This is
on
my podcast.
Every piece of data you've ever looked at.
Right. Well, so the claims are the following. So you have to, in my mind, part of education is you should be able to steel man or steel woman the opponent. So they'll say there are other explanations for the CMB. There are things that we don't understand in the CMB that need to be explained, and including like how do these perturbations get there? How did it get to be so thermal? And then other things can be explained by phenomena, as I said, that are more well-formed, like plasmas are much more familiar than, say, inflation or scalar field that we only know one example of, the Higgs boson. Again, I'm just bolstering my opponent's viewpoint, right? So they'll say there are these problems, and they'll say that light can lose energy, it can become redshifted, And it can make the appearance of all these things. But the worst thing is that these galaxy size tests fail the standard expansionary hypothesis. They're inconsistent. The Tolman test, they fail these so-called Tolman tests. And the only way around those Tolman tests, that the galaxy size doesn't decrease with distance, according to these people, is that, the universe is much, much older than we see it. And so the light has gotten tired by its travel, so some mechanism they don't explain. And, or the fundamental constants are changing, as you said, alpha is changing, what have you, or, or some hybrid. So anyway, obviously the CMB tells us a lot. It doesn't tell us about time equals 0. It only tells us 380,000 years after the Big Bang. But there are lacunae in the Big Bang model. That's the nature of science.
Yeah.
So what these people attempt to do is say these flaws lead to a consideration that maybe the Big Bang is wrong. Okay, that being said, what could or could not these dark stars do to alleviate these hypothetical tensions between the age problem? I had Alison Kirkpatrick on from Kansas. She was the one who's quoted like, astronomers are panicking, because the Webb shows these spiral galaxies. So that is a concern. I have my own take on that. The CMB is dispositive in my opinion, but that the Big Bang happened. But these galaxy formation models, they seem to require some maturation beyond the 13.8 or beyond 300 million years after the formation of the light elements. So tell us, you're the expert in these things. So how could dark stars alleviate or not this problem, quote unquote, of mature early galaxies?
So another way to talk about, the standard model of a cosmology, the 70% dark energy, the lambda CDM model of cosmology.
3 parts.
People, 3 parts dark matter. People have done simulations of structure formation, and you have certain predictions for how many objects you should see and so forth. And so these bloated things that they're seeing early on, where there's all this, what fraction of the baryons of the universe have to go in to create one of these things. I have 2 answers to that. One is, well, we're very happy if some of those are actually dark stars. So let's take away some of the big beasts that you don't know how to explain. Well, we do. So that is, I was actually thinking of mentioning that. Okay. And actually, secondly, there's also the Eddington bias, and I don't know what role that plays in this. This is an observational bias.
Okay.
If you have, there are, let's say, lots more faint objects than bright ones, then it's more likely that a faint one looks bright than the other way around. So in terms of Bayesians, it's not a flat prior. You need to take that into account. I'm not sure. So some people have done that with these galaxies. So that could be part of the explanation. But I'm sticking to my guns. I want some of them to be dark stars.
That would be phenomenal.
We'll take some.
And we'll be the podcast that had you on when. I want to close out because we have to get you over to the medical school to give your colloquium that is so desirable for millions of people to go watch, and maybe eventually we'll get a recording of it.
Now, Brian, can we have a sip of this before we do anything else?
Yeah, absolutely. That's part. Let's get these Irish up these coffees. I want to ask you just 2 last questions. One is about your pedagogical expectations. So I have a rule for my students, including one you're going to meet in a minute, as he escorts you to get your laptop, and that is that my experimentalists, they need to know theory. They don't need to do theory. They need to know theory. They need to know it as well as an incoming theoretical physics graduate student.
Yeah, sounds good.
Not required to do it. And then obviously they have to be world expert in the experimental aspects of the polar bear, Simons Observatory. They need to know that way better than I do because they're interacting with it. I already have my PhD. They don't, right? And I call that the experimental minimum in deference to our good friend Lenny Susskind, who talks about the theoretical minimum. He means something else by it. But I want to ask you, what is the theoretical minimum? Like, you have a new, fresh off the boat grad student. She's coming to Texas. She's working with you. What does she need to know about experiments, if anything?
Oh, about experiments. I thought you were going to say what courses does she need to take?
I assume that's relatively.
All right,
standard.
let's assume everybody's taking the same courses, including quantum
what would
field
you like
theory
her,
and
exactly
graduate cosmology and so on.
Which you took as a high school student.
No.
Didn't you start college at like 15 or
It's 16, partly because my high school had no physics at all, so it was the other way around. But anyway, I survived it.
Yeah.
So I talk to experimentalists all the time.
It's part of your brand. Yeah.
Oh, you have to. So they have to. Yes, I make them do that.
How do you instantiate that?
And
how do you make them do it? How do
well,
you get them interested?
For one thing, we have in our Weinberg seminars, we have experimentalists talk to us. And so that I think is really helpful. And who did we hire recently at UT Austin? We can't just
a lot of people.
We have to hire experimentalists. Yeah. So we hired your former postdoc Nick Galitzky at UT Austin. Yep. And we all go to Weinberg lunches together every Tuesday, and we talk to each other. So that's, I think, really, really important. So that's synergy.
Mixing.
And we have the astronomy department in the same building. You take all in the same elevator, and so we talk to astronomers up there as well. We also we have dark matter experimentalists. Mm-hmm. We have to talk to each other.
Yeah. That's phenomenal.
Yeah.
Last question has become kind of a boilerplate question that I've asked people, changed them since you were last on the podcast. And that has to do with a quote from Sir Arthur C. Clarke. You know that the Into the Impossible name, Into the Impossible, ITI. For those of you who didn't know that, Arthur C. Clarke did a lot of things. He invented the term podcast unintentionally.
He did?
Well, yeah. In 2001, A Space Odyssey, you remember that Dave is going to back in the shuttle to put it back in the space station, and he asks HAL 9000 open the pod bay doors. And a pod became known as this, supporter of information and life sustenance. And then Steve Jobs and one of members of his team took that idea and made the iPod, after which named the iPad after the HAL 9000, seen in 2001 Space Odyssey. And then podcast grew out of the iPod.
Oh, you're kidding.
So that's where it all comes. Arthur C. Clarke also said the only way of determining the limits of the possible is to go beyond them into the impossible. Yeah. So that's the name of this podcast. But he said another thing, and I think I asked you a couple of related questions, but I've since added a fourth law of his. He said the following: when I'm not going to say elderly. I cannot say elderly. When I look at you, I cannot say elderly. But he said something like that. He said when an elderly but distinguished scientist says something is possible, he, and I'm going to say she, is very much certainly correct that it's possible. But when he says something is impossible, he is very likely to be wrong. I'm not calling you elderly, but I am calling you distinguished. I want to use that and ask you, what have you been wrong about? What have you changed your mind about? What has surprised you that you knew
yes,
in an earlier
I'll
time?
give you one.
Tell me.
I remember being at conferences and talking to some brand new graduate student who wrote on a napkin, he writes, lambda equals 0. And we all agreed, the cosmological constant, that's obviously 0. Because there are already observers saying, well, wait a minute, there's something fishy going on, which we could explain if we had a cosmological constant in there. And we all thought, on the theorists, we were like so sure that it was not there. We were wrong. There's dark energy. Well, I don't know if it's cosmological constant, but I don't know if it's dark energy, but there's something weird going on. So we were just wrong. Dead wrong.
Wow.
Yeah.
Well, Katherine Freese, it's such a delight to have you back on the podcast, especially in person. It's been a little while. We did a lovely event in UPenn a couple of years back for our books, and that was a delight.
That was fun.
And I just can't wait to be, now that you're closer and closer than Sweden or Michigan. Now you're in sunny Texas, where we'll have to get you on the pod circuit as well. But we knew you when we only had a couple 100,000 subscribers and followers. Katherine Freese, keep being an inspiration to experimentalists, keep supporting the efforts as a leader, and never, ever give up that wonderful brand that is just so uniquely you. And you're a mentor to me. I mean, we're similar in age, so it's not like I knew you when I was a baby, but you have such an effect on collaborations, and you're the glue that helps keep us together and thrive. So thank you so much, Katie.
Oh, thank you, Brian. It's been great.
Let's get you to your lecture.
Okay.
Thanks a lot. See you next time on Into the Impossible with Brian Keating, your fearful host. And remember, subscribe, find Katie on Twitter, and find her website as well. And we'll have links to her papers and the New Scientist article down below. Thanks a lot. We're out.